All right, guys. We've been taking a close look at the concept of maximum power transfer when it came to a linear network. The idea was you have a linear network and you want to determine what value must the load have so that we can actually absorb the maximum amount of power from the network and have it delivered to the load. Um, Now, we did find the condition, namely that the load impedance can't be the same as the Thevenin impedance, but it must be the complex conjugate of the Thevenin impedance. So that is the condition for maximum power transfer. The one question that we need to answer, and it's the last question that we have left for this part, is, well, how much power is it? So let's go back and answer that question. So here, we're going to take a look at uh, the maximum average power absorbed. And we found that max power transfer trips when the load resistance is equal to the complex conjugate of the Thevenin resistance, or in terms of the real and the resistance and the reactance, it's R Thevenin minus J X Thevenin. On top of that, we had found that the power, which was a function of the load resistance and the load reactance, well, there was a formula that we could use in order to calculate it. It was the magnitude of the Thevenin voltage squared times the load resistance divided by the Thevenin resistance plus the load resistance quantity squared plus the Thevenin reactance plus the load reactance quantity squared. Now, this formula works for every possible load impedance, right? As long as you know the load resistance, the load reactance, you can plug those in. You'll be able to calculate the power. And now we actually want to actually plug in 4. So max power occurs when the load resistance is equal to the Thevenin resistance and when the load reactance is equal to minus the Thevenin reactance. Well, the load resistance appears here and here. So I'm actually going to replace those two with the Thevenin resistance. So here, in the denominator, I have Thevenin resistance plus now Thevenin resistance, quantity squared. And then the Thevenin, the load reactance, that gets replaced with minus the Thevenin reactance. So here we have plus x Thevenin minus x Thevenin, quantity squared. And notice very, 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 very beautifully, a lot of things actually simplify. In particular, notice that this second term in denominator goes to 0 altogether, in which case we have that P max is equal to the magnitude of the Thevenin voltage squared, R Thevenin divided by 2 R Thevenin quantity squared. So I've combined these terms into 2. I can square the 2, I can square R Thevenin. So I have magnitude of the Thevenin voltage squared times the Thevenin resistance times 4 R Thevenin quantity squared. Lastly, one of these cancels with one of those, in which case we get that max power is the Thevenin voltage squared divided by 4 times the Thevenin voltage. This is important to note. This is the maximum amount of power that can actually be theoretically drawn for the network. You can get less power than that from the network, but you can never get more. Worth noting, and this is something that I said at the very, very, very beginning, recall that the Thevenin voltage that we're actually looking for here is the effective or RMS voltage. It is not the magnitude, right? So this whole thing can actually be rewritten in terms of the magnitude, recalling that if you happen to have the RMS value of something, right, um, it is the same thing as the magnitude divided by the square root of 2. And if I actually take just the magnitude of this side, right, it's the same as the magnitude uh, of this side squared. It's the same thing as the magnitude of this side squared. So it is this times its complex conjugate, or it's just the magnitude of this over 2, or the max power of this is the magnitude of the voltage squared now divided by 8 times the Thevenin resistance. So literally what I ended up doing was I plugged this result into there. And notice that since this has a 2 in the denominator, well, this one picks one up there as well. So if you happen to have maybe not the RMS value of the voltage, maybe you just have the magnitude, then you can use this alternate form of the result in order to calculate the maximum power that's actually being delivered. Again, you see one of the reasons why it's so useful to work with RMS or effective values for voltages and currents when you're dealing with power questions. And that wraps up the question of maximum power transfer.